Welcome to Opening Voices. Today, Quentin Adam, CEO of Clever Cloud, is meeting Steeve Morin, CEO and founder of ZML. ZML is a European leading tech company specialized in high-performance AI inference stack. In this first episode, Quentin Adam introduces us to Steeve Morin and his background. They also examine and above all explain the type and scale of calculation required by AI.
Hello and welcome to Opening Voices. I'm Quentin Adam, the CEO of Clever Cloud, and I'm very happy to welcome you in a new episode where we will meet a new tech European leader, which will be Steeve Morin today. Hello, Steve. How are you?
Hi, guys. Welcome. Thank you for having me, Quentin.
So the goal of this podcast is to explain the European technology and business together and try to understand why European technology are not so lame that some people can say, and explain what we are building on our side. Maybe what we can do for beginning is maybe you can introduce you a little bit. What was your life? Where did you work before? Something like that.
Oh, wow. Okay, yeah. To be honest, it's an exercise I'm very bad at, but I'll give it a try because it's you. So I'm Steve. I'm the founder of a company called ZML or ZML, if you are on the other side of the Atlantic. I am first and foremost an engineer. Worked about 5 years on self-driving cars in the early 2000s. Went to a school named Epitech in the early 2000s as well. I'm starting to get a bit old, I think. Yeah, it's starting to show, you know.
We will not disclose your age. But for your 25, you're very welcome.
I am over 25. Yeah, I'm in the down slope, right? Yeah, but then, and most notably, I worked in a company called Zenly for about 8 years. We were bought by Snap in 2017. Then 2022, Snap killed us, and then in 2024, early 2024, founded ZML. We are in Europe.
You also were a guy who acts a lot of cool stuff. You put the code law into GitHub.
Right, yeah.
You built some HDMI key to view some torrent directly.
You remember
on
that?
TV.
Yeah, that's true. Yeah, that was torrent streaming prior to you may remember Popcorn Time at the time, right?
Yeah.
That we're getting old, but prior to that, yeah, I bundled it into HDMI keys. That was the early days of HDMI keys, right? Then it got outlawed. Too bad.
Yeah.
But you know what's funny?
Who think it will be outlawed? Who think?
Not me. I don't know, man.
Who can do it?
Torrenting was, let's just say, useless for a while.
Yeah.
But now it's not anymore, right? Who knew? No, but I always had a soft, place in my heart for a decentralized system, distributed and decentralized system. And torrent to this day is very dear to me. I still donate to libtorrent, by the way.
In Clever Cloud we use peer-to-peer to deploy the system. I think we are the only one to do that, because all of
Alibaba does it.
No.
Dragonfly, that's what it is.
They do it for this part. We use it
But there was a famous paper. Oh yes, and about my background, most notably,
I don't know if you read the
I did, but I've been out for a good while. But in terms of notable achievements, I was the author of Boot to Docker as well, which then became Docker for Mac. Yes, sir.
Yes, Boot to Docker was you also, yeah.
Fun stuff.
Lots of good ideas.
My good friend, Salman. Love you, Salman.
Okay, so and you funded ZML,
right?
What is the reason why ZML is existing?
Because inference is the universal problem, truly universal problem in AI, or at least this was what I was. I would say. What I had to explain to folks, 2 years ago, a year and a half ago, but inference is the true universal problem, and there's no like you have to be radical about it. And there was nothing on the market, as the next operator of ZML, which was, fairly sizable. We were like the number one spender on Google Cloud for 3 years. So we had quite an operation. And as, next operator of that company, of that infrastructure, right, there was nothing on the market that, was something I would feel confident, deploying. And it felt to me that we were in this, very uneasy situation in which, either you pay money to Sam Altman, which, I would wager he has, plenty of, or, you pay money to Jensen. But I didn't see anything fundamental about this, right? Yes, there's CUDA. Yes, there's thank you. There's CUDA. There's, the networking and all of these stuff. But it's not for lack of, like there's offer of chips. Like there's AMD, there's TPU, there's Trainium,
Okay. What we can do maybe to help anybody understand what we are doing there is explaining how those work I. What we call I, which is a subset of I, which is LLM.
Right.
How does an LLM work from a calculation point of view, and which phase are happening in a calcul, and which kind of calcul are we doing, and why does it not fit in the plain old Intel we all have in our computer?
It actually does in some weird way. So I mean, first things first, right? Maybe as a bit of context before, I explain a bit, how they work at the very broad but, very fundamental level is we haven't been, compute bound in 20 years. We used to be compute bound, but since, about 2005-ish, we were network bound, IO bound, right? Which then made the cloud, made the whole...
Make all the first well-known talks about Clever Cloud explaining to the people that anywhere in the world we have IO problem. Just stop talking to me about calculation in your CPU. You have problem of network and storage.
Rails, right? And Python and so on. So it worked beautifully for like 20 years, right? We were limited by networking, whether it's, and storage as well, but IO in general, indeed. And whether it was, internal networks or like external networks, like 5G and all of these things, right? Well, I would say wireless networks. Mostly an IO problem. And then, what have you? We go back into compute-bound problems, right? There's so much thing, like a GPU, let's say, or a CPU for that matter, can do. And so all this infrastructure, like software infrastructure that we use for like 20 years, or at least 15, let's just say, or like, 10 if you, count Docker as the start of, the new generation type of thing. I know you have a sweet spot for that technology.
I think it's I will say it like Go. Docker is a very, very nice technology for a technology from the 80s, but yes.
Remember Solomon is my close friend.
Yeah.
Right? But in all seriousness, like we were essentially IO bound, and we are now going back into compute bound problems. And so a lot of things are, thrown out the window. Knowing this, there's very little, reuse in terms of software infrastructure. We try to, but it's very hard. And so everybody's trying to figure out. And so in the very,
but the reason why we are computation bound in the CPU bound and compute bound in this world is maybe because we change the way we make calculation. What we does with LLM in kind of operation is quite different of what we were used to do, isn't it?
Let's just say that calculations, those types of calculations are not very different in the sense that they were always there. Like, it's just that compute became good enough for it to be viable, right? So it's not a new thing. Like we, reinvested.
But there is a reason why we're using GPU and not CPU is because
mostly because of matrix multiplications. Yeah, but
it's a kind of calculation we don't use a lot in a traditional computing system.
So yes, but maybe like GPUs, what they do is they put us ahead of the curve, essentially. One could argue that those types of calculations, especially in HPC, for instance,
I always been there.
Yeah, well,
But then there is a generalization of the point.
Oh yeah, absolutely. Yeah. But the idea is there's very little reuse. There's new hardware, obviously, and maybe something that's new today is now we have to care about the hardware because we are compute bound, right? So,
but because mostly we're using majority of instruction, we use very little before.
Of the hardware, you mean? Oh yeah. We spent most of our time waiting, so we could abstract it away. This is the thing. You could abstract the hardware because most of the time you were spending waiting for I/O to complete. But now it's not, number one, that's not the case anymore, and number two, you have to care about, essentially you deploy on this precise hardware, right? I recall a time in which, deploying, or let's say, having a 486 DX2 or a DX4 was a very big difference, right? But, if you look at your average, cloud deployment, they use 8-year-old CPUs and nobody cares, right? Because in the end, we are indeed waiting on I/O. And so today, the issue, we're running again into is
it's
we have to care about these things.
Maybe we can explain.
And so,
if I ask something for a network, what will be the kind of different step which will be happening inside the system?
Essentially, the way it works, the way it works is you can imagine you have what's called the latent space, right? And the latent space is, where all the information, lives, right? So for sake of simplicity, let's take a 3D space, right? And in that 3D space, you can model everything, let's say, right? So in LLMs, it's a lot more than three dimensions, but, for sake of simplicity. So maybe, you have animals here, right? And animals, you would have, dogs and cats, and that sort of thing. In this space, essentially lives, knowledge, but also, vocabulary, everything, right? And so what you do, essentially, is you have a vector in that space, right? You have a point in that space, or rather a vector, right? Mm-hmm. And what you do is...
So you vectorize the information first?
Well, let's just say you have what's called a vector representation. So it could be usually we call it an embedding, for instance. But the idea is, for sake of simplicity again, you have a vector, right? Representing, let's say, your query. Or your current token. And you're trying to generate the next token. Token is a bit, of word, right? Yeah. And
it's kind of a syllabus for people to understand, because we can have people which are not technical looking at the video. So basically,
imagine, a token is
first, if you try to request a LLM, first you will cut your sentence into.
So you divide your sentence, let's say, into syllabus, right? So 2-3 letters,
It will be what we so-called tokens.
Tokens, yes.
The thing you don't understand, but you pay.
Pay for a lot, right? Yeah.
The tokens. It's more or less the syllabus.
And the idea is, what you do in those tokens is you try to predict the next one, right? So when you ask a question to an LLM, you divide the text into tokens, and then you essentially register, the transformation between the text you input. That phase is called a prefill, right?
Okay.
And then you ask the LLM, generate the next token, right? So, but you might ask me, but this is not what I'm doing. I'm asking it a question, right? I'm not, generating the next token. Well, you are, because what you don't see is that in the background, there's your question is prefixed by, let's just say, question, the question you just entered. Then the system will append, response, and then let the LLM predict the response, right? So what happens is, and then you generate, those tokens. And so how does it work? At the end of the last token, you can represent it as a vector, right? And to generate the next token, you will apply transformation on that vector. And so these transformations happen in sequence. These sequences are called layers. And so for each layer, you will, take the input, apply the transformations, go to the next layer, reapply transformations, right? And each layer is a series of transformations, but the same always, right? At the end, you get another vector transformed by, the sequence.
The sequence of layers.
Yes, and what you
How
do...
many layers can you expect from at the day a classical LLM like GPT-5?
So GPT-5, it's not public, but if you took like a Llama 8B, for instance, 8B means 8 billion parameters. So there's 8 billion parameters that are, essentially applied to your LLM, to your vector, sorry. It's 32 layers.
32, okay.
But it can go into 80, 100, What's important though is that you run these layers in sequence. So there's a causality aspect to that, right? You have to do one, then do the other. So you cannot parallelize,
You cannot
this.
parallelize the stuff, okay.
All right. Now that we know this, in the end, we get another vector, right? And so what you do in the end, you take your big table of syllabus and you try and find the closest syllabus to that vector. And it's called detokenization.
Okay.
And this is how you get the next token. You apply that token and you restart the cycle over again. Well, you don't start from the vector you just found. You start from the token.
And
Yes.
how do you decide you have enough token? You made a sentence or something like that?
So the model is trained to essentially self-limit itself. So you have a contract with the model it's called a template. And the model may have special tokens to tell you it's done finishing. Okay. But it is up to you to actually do it. You can indeed, what model can signal to you that it's done, and you can tell it, yeah, I don't care, do it, continue. And it will continue until, a lot of times what happens, these models, like they start to loop and they repeat themselves over and over again. All of them this can happen, but in the end, yeah, you have to have a contract between...
Like a long speech of Donald Trump.
A bit more coherent, but yes. But yeah, no, that's the idea. So you have a contract in which the people who train the LLM tell you, all right, this is a special token to tell you that this is the user input, for instance. This is a token to tell you that the model was trained to think that the end of that response is the next probable token, and so that's how it works. And so you have to act on it. Of course, you have to detect it, and then stop generation.
And so
that's how it works, right? It's not very.
What is the kind of operation you do to generate your tokens? What is the kind of
what do you mean?
What is the kind of instruction you give to the computational chip?
Many things. So there's many. Usually they are like bricks, right? What's you have the multi-layer perceptron, the attention layer, the activation functions. There's like many essentially a game of Legos, and you assemble them.
So the layers are not making the same thing all together.
The layers are the same. They do the same thing. So usually it's tokenizing, embedding, layers, detokenizing. And
what
this
do
is how you get the
embedding?
token.
Because
embedding is like
explain this to the guys.
Embedding is like transforming the syllabus into its vector representation.
Okay.
So it's like the table.
So we tokenize. We put it into.
So let's say you
vectorization.
Quentin Adam, right? Let's say we tokenize you into 2 words, right? Then why Quentin? Why not why not letter by letter or that sort of thing? You don't know what a tokenizer is trained, right? So it will try to find, ways to essentially represent most of the text in the less, amount of space. So the idea is, let's say we tokenize you into 2 tokens, right? Quentin Adam, right? Quentin will have a vector representation in that space, right? So there will be so we will have a table of 2 entries. One is Quentin, one is Adam. And maybe another one is Steeve and Morin, let's say, right? What you're embedding is going from Quentin to the vector. So it's a lookup. So embedding literally is like looking up, all right, for Quentin, this is that vector. And in the end, when we generate, we will take, the output vector, find the vector who is the closest. Oh, it's Adam. Off we go. This is Adam. And that Adam becomes the new starting point for the generation. But layers are the same, and layers are a sequence of operations, right? So usually there's like 3 bigs, let's just say. MLP is one, multi-layer perceptron is one, attention is a big one. Attention is for transformers. Transformers are what
is the attention phase? Because maybe we'll...
So attention is trying to figure out, the idea of attention is that not all words are the same, have the same impact, right?
So attention,
so let's say
when you decide what is the important...
Roughly, yeah. The idea is, let's say tonight I'm doing a podcast with Quentin Adam, right? You realize that, Quentin Adam has more, I would say, weight to that sentence that I'm, right, or doing, right? And so attention sort of represents that, right? And so the idea is like the model will try to what's called attend to words that are important to try and generate, the next phase. But the idea is, in the end, you run these layers in sequence, detokenize, and you start all over again.
It's a lot of calculation to do.
Yes.
That's way a lot of calculation. That's just like, for example, understand SQL request, put it in an engine, store it in a.
Yes.
It's.
But it's not.
What is maybe it's a stupid question, but what is the kind of ratio of number of calculation if we go on pure number of CPU requests? But
I know.
Can we say just like it's not the same amount? It's not the.
No, it's like
it's not the same world. In fact,
millions more.
It's billions more. Billions more.
But
so it's way a lot of calculation.
Yes, but you have to understand one thing that is very important to understand about essentially neural networks and say AI in the way we talk about it today is that these behaviors are like emerge from it. So what you do is you assemble Legos and you hit it enough that behavior emerges. So it's not like something you bake in. So it's hard to say whether we should do 100 million more calculations than 10 million, right? Or
it's just I'm trying to make people realize why it's so a big change, and why it will be a change from a financial point of view. So I'm trying to figure out to the people that why AI is not traditional IT. And what's different? It's not just a simple software we put.
Right. So
and that's why I'm asking this kind of question, saying like, okay, can we make the difference? Because like sometimes we say to the people, we switch to C to Java, and it's different because we switch from a static language to interpreted one. And yes, there is a few more calculation, but we win a little bit because of just in time and stuff. And so we roughly will cost us like 30% more requests to the CPU, right. And that's it. But there we are not talking on the same amount of needs,
Right. This is true, but so there's a few things. One is, number one, my bet, or at least my goal with ZML is that we get to reuse, a lot of that infrastructure. But
we will explain that.
No, I know. But the main, fundamental problem is that these tools were built on assumptions that don't really hold for AI. One is that indeed we are compute bound. Yes. The second assumption, so that is a new thing, right? And it's different from, overloading your production. It's very different, right? Because at some point the chip, the numbers a chip can do are not very large, right? We're talking like, tens of people at the same time, not 100, right? So imagine you have to do web with a server that runs at like 16 people requests per second, that's not a lot, right? Or can serve, at most, 16 people at the same time, right? You can imagine, like, this is a ballpark.
Like launching free mobile.
I love them. I love you, Xavier. But the thing is, this is one thing. So compute bound. Second, of course, the amount of money that you have to spend for what you get. But the kicker is, so this, by the way, all this infrastructure, this software infrastructure was built on those assumptions, right? So there's adjustment to be made. The last one, and probably the nail in the coffin, is that LLMs, or at least AI in general, is stateful. The state of a model has to be kept somewhere, and that state is fucking big, right? We're talking for like average conversation. Well, actually, I can give you a number. Like we're talking like, 200 kilobytes per token of state that you have to keep.
Per token. And an average conversation will be
a few thousand tokens.
A few thousand
if you count the system prompt, etc. So there's ways to mitigate that, page attention and so on, but that doesn't change the matter. The matter is that state is big. That state, but that state is big. State is called the KV cache, right? And the KV cache is the rock in your shoe. It's big. It's kept in the most premium asset of modern computing, which is GPU memory. And did I say it was big? Because it's fucking big. And so you cannot freely move it around.
And
right?
At the beginning, the GPU was not so rich in memory, because
yes.
in the traditional GPU usage, we don't need a lot of memory. We need a little bit of memory, a little bit.
Of course, because you do what's called dense calculation.
Yeah. And we have like very few storage to do and stuff. So what we learned this week, because the podcast is divided in weeks, so it will be like several episodes. So what we learned this week is basically one of the big points of AI. It's a leapfrog in the number of calculation we need, and it's kind of calculation we didn't used to, and that's part of the problem ZML is trying to resolve.
Yeah, but here's the thing: there's one piece that that gets overlooked, not by the people who run these systems in production, because they realize it's a very sour surprise, and that surprise is because the state is so big, you cannot freely move it around.
Yeah,
which means you have to keep it where it is. Which means your system is now, have to be stateful, and it has to be fragmented. So you run into fragmentation issues, you run into subscription issues.
You have to have sticky session.
Absolutely.
Which is an anti-pattern for the last 20 years.
Because if you rebalance,
you need to move the fucking context.
Yes, and so
the KV cache will not.
By the way, for the people who had to operate Kafka in production, they know what I'm talking about, like what a rebalance can be painful. But it's the problem with AI.
It's worth for absolutely every distributed system.
The problem in AI though is that essentially you are between a rock and a hard place. There's two solutions to that. One is you transfer the data, but you very much get the risk of overloading the network, essentially, shooting yourself in the foot. Or you say, you know what, screw the state, I'm going to recompute it. Good luck, because you are already compute bound.
Yeah.
So there's no free lunch.
And the other point is, if you transfer the state, the silicon you pay expensively will be moving data around instead of making calculation.
You can get away if you buy the fully integrated NVIDIA, blah, blah, blah. So you can overlap.
We can explain this next week. So next week we will explain the difference between inference calculation and training calculation.
Oh man, like the thing is, they're not so different in terms of how they operate, in the sense that, training is two passes, forward and backward. It's called the forward pass and the backward pass. Inference is running only the forward pass, right? So you can do inference with training infrastructure.
We were trying to explain the kind of calculation we're facing at and what kind of solution can offer ZML. So thanks for following us. We're going in a deep conversation about the new principle of AI computation. See you next week for the next episode with Steeve Morin.
Thank you for listening to Opening Voices. The conversation between Quentin Adam and Steeve Morin will continue in a few days, so follow us and subscribe not to miss our next episode.